Today we'll be talking about section 4.3, which is about other discrete probability distributions. So in 4.2 we were talking about the binomial distribution. And the binomial distribution is a very powerful probability distribution, but it doesn't cover every single situation that might arise. You might be looking at something from a slightly different angle. Maybe you're not looking for a certain number of successes. Maybe you're looking for something else entirely. So let's look at an example. The probability that a potential driver passes the DMV written exam is 72%. What is the probability that a randomly chosen test taker doesn't pass until his or her fourth attempt? So this is different than the binomial, right? We're not looking for a certain number of occurrences. We're interested in the first occurrence, right? When is the first time that person passes the DMV written exam? Because once they pass it, they're not going to take it again. So it wouldn't make sense to ask questions about what's the probability that the person out of 10 trials passes the test 7 times. That doesn't make any sense because you're only going to take it until you pass. So for this person to pass for the first time on the 4th attempt means that they must have failed the first 3 times they took the exam. So we can use the multiplication rule that we talked about in Chapter 3 when we were learning counting. And so we look at it as a bunch of slots to be filled in. Okay. We said that this person has to fail on their first 3 attempts. So if they fail, they fail, they fail, and then they finally pass. So the probability that they fail is 0.28 each time, because each test is independent of any other test. As a matter of fact, in the DMV test, you may be taking different versions, right? So you're not necessarily taking the same test twice. So you might be able to make an argument that when you're taking a DMV test, you should do better the next time because you've already seen the questions. But with those DMV exams, you're taking different versions of the tests, so the questions aren't necessarily the same. So we get probability of failure being 28.28 again, and again another 0.28. And then if it's a 28% chance that they fail, it's a 72% chance that they succeed. That's where we got the 28s from, is that we were told it was a 72% chance that they succeed. So according to the multiplication rule, we're going to multiply these together. And when we do that, we get 0.01580,544. This concept leads us to a new kind of distribution. It's called the geometric probability distribution. So in 4.2, we talked about binomial probability distributions. Now we're moving on to geometric probability distributions. But it is also a discrete probability distribution. So a geometric probability distribution is any probability experiment that meets these conditions. You repeat the experiment until success is achieved. Each trial is independent of any other trials. And our probability of success, which we call P of S, is the same for each trial. And so we have a formula. The probability of first success on trial X is given by Q to the X minus 1 times P. Why is it X minus 1? Well, we're talking about succeeding on trial X. So if X is 12, if the first success is on the 12th attempt, then that means the first 11, which would be 12 minus 1, would have to have been failures. Our notation is that P is the probability of success, Q is the probability of failure, and Q is 1 minus P. Okay, so let's take a look at an example. All right, we got Shaq. Over his entire career, Shaquille O'Neal was a 63% free throw shooter. During a single game, O'Neal attempted 11 free throws. What is the probability that his first made free throw attempt is on the 3rd attempt? Now, for those of you who are familiar with the NBA and maybe have watched basketball for a long time, you may know about Shaq. Now he does car insurance commercials for the general. But when he was a player, he was a terrible, terrible free throw shooter. So bad that teams actually developed an entire defense around the fact that he couldn't shoot free throws very well. And what it was is anytime Shaq had the ball, if they were down and they were trying to come back, they would go foul Shaq, send him to the free throw line, and chances are he was going to miss. They used to call that hack-a-Shaq, right? And so it allowed a lot of teams to come back when they were down, right? If you're down by 10 or 12 points, you start playing hack-a-Shaq, and all of a sudden, you're not trading 2 points for 2 points going up and down the court. You're coming out ahead each time down, because if Shaq's shooting the free throw, chances are he misses. Anyway, so how do we solve this? This is a geometric situation, right? Because we're looking for his first made free throw. And we want to know what's the probability that his first success was on the third attempt. So that means he must have failed the first 2 times. So that's going to be failure to the second power times success to the first, which is 0.37 to the second times 0.63, which is 0.086247. So I've got a practice problem for you. One game at a carnival involves tossing dimes onto stationary plates. The probability of a player landing a dime on a plate on any toss is 0.2. What is the probability that a player's first success will be on the 8th attempt? I love this game. I play it every time I go to the fair. I won all kinds of glasses at the last Fresno fair. Anyway, so take a look at this problem. Try to apply those geometric formulas here. Pause the video to give yourself a chance to work, and when you're finished, hit play. Okay, so this is geometric for sure, because we're looking for the opportunity to make your first successful throw on the 8th attempt. And so if your first success is on the 8th attempt, then you failed 7 times. So if the probability of success is 0.2, then the probability of failure is 0.8. You would have failed 7 times, so you're going to have 0.8 to the 7th power times your success, your 0.2. The success will only happen once, because you're not going to go past that first success. So you get 0.8 to the 7th times 0.2 to the 1st, which is 0.04194304. So that's geometric. That's another probability distribution, another discrete probability distribution that's different from the binomial. There's another one that we want to talk about. And it doesn't fall into the binomial category. It doesn't fall into geometric category. So what if instead of the number of occurrences or the timing of the first occurrence, we wanted to know the probability of a set number of occurrences in a certain area or time frame? So in an interval of time or space. Right? So you might be interested in the probability of a certain number of hurricanes in a year, a period of time, or the number of missed stitches per square yard of fabric. So that's an area of space, right? An interval of space. For this, we turn to a distribution called the Poisson distribution. That's Poisson, not poison, Poisson. In French, Poisson means fish. So at some point in his life, Henri Poisson, who is the person who this distribution was named after, someplace in his family there was a fisherman. And so that's how he got his last name. Okay, so let's look at the Poisson probability distribution in detail. It's a discrete probability distribution that follows these rules. First, the experiment is counting the number of occurrences in a certain interval of time or space. The probability is the same for each trial. The number of occurrences in one interval is independent of the number of occurrences in any other interval. And we have a formula for the probability of exactly x occurrences in an interval. And that's given to us by the probability of x is mu to the x e to the negative mu over x factorial, where e is the natural number and 0 factorial equals 1. We mention that here because if you're asking a question about the probability of 0 occurrences, you'll get a 0 factorial on the bottom of this fraction, and you need to know that it's equal to 1. When you look at that formula, mu we've seen, it's a mean. X is the value of the random variable. What is this E number? Okay. E is what's called the natural number. If you've heard of the number pi, 3.1415926, pi is a number that goes on forever and ever and ever, and it never repeats, and it never ends. Well, E is similar to that. It's 2.1878 something, something, something. So, and it does the same thing. It goes on forever, and it never repeats. The reason it's called the natural number is because it's this ratio that keeps coming up as we investigate natural phenomena. Things in biology, things in chemistry, things in physics. This E number just starts popping out, just like pi does whenever you're investigating any kind of circle. So this is that natural number. Okay, so let's see how this would be used in an example. So, in Madera County, the average number of potholes in any 1 mile stretch of road is 4. A 1 mile stretch of road in Madera County is chosen. What is the probability that there are exactly 6 potholes in that stretch of road? I guarantee you, if I'm driving on the road, the probability is 1. So let's look at a solution. This is Poisson. The reason that we know it's Poisson is because we are looking for a number of occurrences within a single mile stretch of road. That's an interval of space. So in this case, mu is 4 because it said the average number of potholes was 4. And we're interested in the probability that x is 6. So we apply our formula. Probability of 6 potholes is given by mu to the x, so that's 4 to the 6th, e to the negative mu, so that's e to the negative 4th, over x factorial, so over 6 factorial. When we plug that into our handy-dandy calculator, we get 0.104195646. You should try to plug it into your calculator to make sure that you're getting that value. If we rounded it off to 4 decimals, we'd get 0.1042. If you're entering this into your calculator, the best way to do it is to start with the E. Now the E on the TI 8384 graphing calculators is a second function of the button that says LN, which is on the left-hand side of the keypad. So you would hit second and LN, and then it'll throw up E with a power, and then type in -4. At that point, just hit enter. It's easier to do that way. And that'll give you the value of e to the -4th. Then press times, and then type in the 4 to the 6th power. Hit enter again, and then divide by 6 factorial. And so to do 6 factorial, you would type in the 6, hit the math button, and go down to the exclamation point, hit enter, and then hit enter again to get your final answer. So we've got a little practice problem for you. I know it says example, but it's a practice problem. The average number of hurricanes that make landfall in the United States in a calendar year is 3. What is the probability that there will be 5 hurricanes that make landfall this year? And then what's the probability that there will be no hurricanes that make landfall this year? So pause the video, work it out, and when you're ready, hit play. Okay, so let's take a look at the solution. We've got 2 separate problems here. So for the first one, we're asking what is the probability that there will be exactly 5 hurricanes? So the mu in this problem is 3, and the x in the problem is 5. So we plug this into our Poisson formula, and the probability of 5 hurricanes is given by mu to the x, so that's 3 to the 5th. E to the negative mu is e to the -3 over x factorial over 5 factorial. And so this is equal to 0.100818834. And we would round off to probably to 4 decimals, 0.1008. For the second problem, again, it's Poisson. But this time, the mu is 3 and the x is 0, because we're looking for 0 occurrences. So according to our formula, it's going to be mu to the x, so 3 to the 0, e to the negative mu, that's e to the negative 3, over x factorial, that's 0 factorial. So this is where that little blurb came in when I introduced the Poisson probability distribution, and I said sometimes you have to know what the value of 0 factorial is. 0 factorial here is 1. 3 to the 0 power is also 1. So this is 1, e to the negative third over 1. So really, you're just computing the value of e to the negative third. And if you typed in e to the negative third, you get 0.0497870684, which is 0.0498, rounded to 4 decimals. Okay, well, turns out that the Poisson probability has been compiled into tables, and you can find those tables in your textbook. The mu values run from 0.1 to 10.0 by tenths, and then from 11 to 20 by ones. And it provides 4 decimal place accuracy. But the TI-8384 also will show you how to do this. And so we go to that second function in the vars menu, just like we did for the binomial distribution. And this time, when you get to this screen, you're going to scroll down until you find Poisson PDF. When you find Poisson PDF, you hit enter, and a couple different things could happen depending on the version of the calculator that you have. So you're either going to see Poisson PDF show up on your screen, or you're going to see Poisson PDF with a weird symbol. By the way, that's a lambda, an x value, and a paste. So if you have the older version, which is the one on the left, then what you're going to do is after the Poisson PDF, you're going to type the value of the mean, and then a comma, and then the value of the x, and then end the parentheses. If you have a newer version of the calculator that gives you the Poisson PDF with the lambda, x value, and paste, you'll type the value of the mean for lambda, then type the x value, and then highlight paste and press enter. In either case, this will show up on your screen when you're done. Okay, Poisson PDF 3, 5. And if you hit enter, then what pops up on your screen is 1.08188.134, which is exactly what we got to the first part of that practice problem. Okay. So we've got one last example here. The average number of minors arrested in Madera County for violent crimes in any given 30-day period is 5. A 30-day period is chosen at random. What is the probability that there are exactly 3 minors arrested for such crimes in that period? Use the table and calculator to find your answer. So use either one, either the table or the calculator. The table is built into your book. Now, most of you don't have a physical book, but on the Pearson website, whenever you're in the homework for a section, you can always go to the menu on the side in the homework player, and one of those options is textbook, and you can find the Poisson tables in that textbook. Okay, so in this case, is it Poisson, first of all? Well, are we looking at an interval of time or space? And because we're looking at 30-day periods, that's an interval of time. And so when we're finding probability of something, a certain number of occurrences in an interval of time, then that means it's Poisson. So we can tell the difference between mu and x because mu is going to be the average. So in this case, they told us the average was 5. And then we were specifically asked, well, what would be the probability of exactly 3 occurrences? So, if you're using the table, you would find the 5.0 column on the table and go to the row for x equals 3. And the result would be that you would find 0.1404 as the table value. So that's your probability that exactly 3 minors were arrested in Madera County for violent crimes. If instead you were using the calculator, you would go ahead and type in Poisson PDF 5,3. Again, depending on the version of the calculator you have, you're either going to have the Poisson PDF and have to enter the 5,3 and end the parentheses, or it'll say lambda and x value. The lambda would be your 5, the x value would be your 3. This would show up on the screen. And when you go ahead and enter that into the calculator, you would get 0.1403738958, which of course rounds off to 0.1404. So the table, the calculator, they're going to give you the same answers. Alrighty. So that's going to bring us to an end of section 4.3. Please look on the Pearson website for your homework, and have a great day.